There it goes. All right. Let me make sure I got the slides on up. And I'll start sharing my screen.
That's fair.
And I'm probably going to be looking up at the TV the entire time. So because the PowerPoint won't let me see, things and people, but the TV will. Everyone can hear us and all that, correct?
Yes.
Excellent.
And you guys have a full screen of the Landsat Stella splash screen, correct?
Yes.
Yeah.
Excellent. All right.
So now we're waiting for people to join.
Yeah, I figured we'd probably start like 11:02, 11:03, just in case
Sure,
people were.
sure. We'll give 5-10 minutes to people.
Yeah, give them a few minutes to come in so they don't miss the beginning, my intro, and all that sort of thing.
Will you see if people are logging in?
Huh?
Do you have to let
We would
them in?
need to
Sometimes
Yeah.
stop the sharing.
Yeah, we need to stop the sharing. I'm just going to assume that they're going to log in and check it out. So
they don't need your permission or something.
no, just the panelists need my permission. The rest of the stuff was, we were able to get in without, doing much. Yeah.
Well,
And anyone on our core team, so Ross, Paul, Nyssa, and anyone who says it. We cannot see any hands that go up from the chat currently. So if there is one, let us know. So we can answer questions.
But questions are going to come at the end.
Yes.
Like I said, I want to try and keep this to a nice tight 20 to 30 if we can. And then the rest of it will be questions. Okay. All right. So. All right. And it's about 11:02, so I guess I will get started. So welcome to the Landsat CPE Presents Stella webinar here, and we're going to be giving some updates as to what's going on with Stella. That's right, and I keep forgetting that the thing's over there. Sorry, the PowerPoint's up on the screen over there, so you're going to see me looking over there quite often, and I apologize for that. It's just the way this place is set up. Okay. Now, I should introduce our team a little bit. See, I am Mike Taylor, the team lead. We have Paul Murrell, the creator and inventor, Dr. Petra Campbell, lead scientist, Jesse Barber, Cal Val, Ross Walter, the programmer and visualizer. And then we have our sort of unofficial team members that are awesome, Paige Williams and Dr. Nyssa Rayne that are joining us as well. Okay. And like I said, we'll be going through some of the latest and greatest with Stella. If you want to find out, a bit more, we do have the recording of the webinar that we did previously, where we sort of introduced all of the Stella available and up online. So, and if you can't find it, we can always send you a copy. Thank you. See, so again, like I said, here's the team introduction. So this is a bunch of us doing some of these various activities and teaching about how we can use Stella in the classroom and so on and so forth. Okay, so general updates. Okay, so we had Allison Leidner use the Stella with the astronaut candidates recently and had them learning all about some earth science and collecting data and all that. So that was pretty awesome. Peter Nelson also has been using the Stella with the moon trees for GLOBE. Okay, and that webinar is all up as well, and it's got me talking as well. Hopefully not quite so fast. Let's see, we had 2 interns over the summer that built 40 of these Stellas, and we have been loaning a case of 2 of them out to people this over the summer, and we're trying to basically, collect some use case scenarios from them, and as well as, of course, introduce them to Stella and all this sort of fun stuff that they can help do with their class and all that. All right. Let's see. Yeah, and the Stellas have been basically again handed out across the country. And of course, if you want your own Stella loaners, you can go ahead and email me, and I will try to get some to you as soon as they become available again. Okay. And again, it's been across the country, across multiple different disciplines and different grades, from middle school on up. And so we look forward to seeing, basically how people use them and all that. On the website portion, I have added some data collections. So we got some Stella data collections. That's multiple Stellas looking at, the same stuff, and then looking and comparing it against stuff that, basically, is similar in color and all that, but it might not be the exact same material. So, you got like grass and green construction paper, or, say concrete and the polystyrene, and so on and so forth, as well as some raw data and such up there as well. Okay, and we have a lot more coming, but sorting all the data and getting them into nice, neat collections takes a bit of time. So Stella in the media. So recently we've had about 3 stories that went up about different things going with Stella. One of them, of course, being which our lead scientist, Dr. Betsy Campbell, with Fred, I believe. So you had some notes from the field going up. And we had a 50th anniversary with that Ellie McGinty was wrote, which was just amazing. And then Rob Gardner and his interns Nora, they wrote a nice story about Stella, comparing it sort of to a tricorder. So that was just really, really amazing. Okay. What we are working on, an amateur spectral library, and I've actually made a little bit of progress on that, and we'll keep you all up to date as to what's going on with that. Hopefully in the next month or so, we have a bit more collaboration going on with that. Large area calibration. So Jesse, being the awesome person that he is, and of course Paul, and just sort of the team going around and thinking of ideas of how to do like sort of a larger area calibration and all that, have come up with some really fun ideas. So we're going to be testing those out, and then instrument improvements and all the other fun stuff coming on. You will want to stick around, and especially till around the end, because we have some really exciting new announcements. Okay, and with that, I'm going to hand it over to Jesse, and he can talk about what's going on with the Cal-Val of Stellas.
All right. So yes, my name is Jesse, and I've been doing all of the Stella Cal-Val things as they've been going on. The majority of the units that I've been working with are Stella 1.0. So they look like this, have the same sensors, but are far before this. We started what, 2 years ago almost?
Almost.
So pretty much right at the beginning there, I got a bank of 5 and then 10 Stellas, and proceeded to just do regular calibrations on them and just take data in the same way with my calibration setup on my sphere to see how they react and see how they go. As you can see in this graph, we have 2 types of charts, one that is a nice smooth line and another which is a set of dots with error bars. The dots are the Stellas and the bank of Stellas that we have, which you can see in the legend, and the line is our ASD that we are using as a cross-reference truth. So the curve that you see is the ASD. The axis on the right is the ASD axis, and it has slightly different units than our Stellas. Our Stellas work in irradiance and our ASD works in radiance. And the only difference is how much per steradian you have. So irradiance is dependent on distance to the object. Radiance is independent of that. So while we are unable currently, and we're currently working through the math to get them to mesh up, you can see from just the general curve that our Stellas do follow what it should be. And after we do the math, we'll be able to get calibration coefficients, and we will be able to match these up much better. On the bottom, and the large red dots in each of these is the average total ensemble of the entirety of all the Stellas. I was unable to put the error bars for each individual Stella on there and make it look good. So the errors for each individual Stella are on the next slide. So as you can see here, we have a fair few less of the Stellas, and that's because as we went through, and that bank of 10 went down to a bank of 7, because we've had some corrosion issues, et cetera, but that we figured out was due to faulty solder that we used at the beginning,
My fault.
et cetera. And all of these have been, all these issues have been buffed out at this point. But as you can see, with the standard deviation divided by the Stella average, and then translated to percent, our units are very good. Especially some of the units specifically, like 2479, it is less than half of a percent half of a 1/10 of a percent of variance divided by the unit average, which is quite good. We decided to use this way of error just because it is similar to what I use in doing my own ASD measurements, and it's similar to one of the ways that NIST does their stuff. And in the bottom right corner, you can see the setup of my sphere shining onto a reflective surface, Spectralon in this case, and then our Stella set up to catch that instant light. And that's the calibration process.
Okay, and now we're going to go on to Paige Williams, our delightful drone expert and wonderful person all around.
Thanks, Mike. So I'm Paige Williams. I'm a PhD student at Virginia Tech. I kind of work on the student outreach and education outreach side of Stella, and also incorporating it onto drones because I have some experience with drones. You can move to the next slide. So I've done a few things here at Virginia Tech, and amongst the workshops that we offer something called GeoTED, which is geospatial workshops geared towards high school and community college educators to learn how to use remote sensing in their classrooms. And I used the Stella in the classroom this year, and it was a big hit and got them very excited, and it really helped explain some of those remote sensing concepts that are sometimes hard to explain just through some PowerPoint slides. So giving to them some hands-on things to do was really awesome. And I've also worked on this with my forest photogrammetry class, which is a remote sensing course at Virginia Tech geared towards juniors and seniors that are studying forests. And here at Virginia Tech, we've put together 5 Stellas to be used in workshops or classrooms and such. Next slide. And another thing I've been working on is putting the Stella on a drone. So the first thing I did, which is very rudimentary MacGyver way to do it, is I used some duct tape and just simply duct taped it onto the bottom of a DJI Air 2S. This is a very light, very durable, sport-like drone. And Paul has also worked in the bottom right. You can see those future drone accessories that are going to be applicable to different types of drones where we can mount those sensors onto the drones. And even with this very small drone, the sensor is very light and it's able to fly with the sensor on it. So that's very exciting.
Thank you, Paige. And next we will go on to Dr. Petya Campbell, our awesome lead scientist
Well,
and wonderful person all around.
Thank you.
Mhm.
Well, it has been a lot of fun and a pleasure working with the Stellas. And so we started at the beginning of the year measuring in cold conditions, measuring grass. And after that, we went to Alaska and measured snow and trees with snow and other things. And when coming back, there were the students. So together we had a field experiment measuring different plants with different function, different amount of chlorophyll or biomass, green biomass together, and we try to compare these measurements with the stellas, with the measurements with the standard field spectrometer like the ASD, and you can see here the team getting the calibration measurements, getting the targets, and then going back again. And so the group was quite large, included Jesse, Mike, Fred Humerick as well, and summer students. And so we all reasoned how to do it with the goal to decide on the best way to get comparable measurements, and that's a challenge. The field of views of the instruments are different, like the ASD and the STELLA see different things, so we need to position them to see the same vegetation, then to see the targets, and so so far we have been quite successful. We can go to the next slide. Looking agricultural crops, which have less variability in the canopy. And so we can compare, although there is some offset after we calibrate the stellar to radiance and reflectance to the ASD reflectance. And they're strongly related if we are looking at targets. So the first one is looking panels. And then when you go into the vegetation, it's more diverse. And we cannot, in the middle, you have vegetation indices, and then on the other side, you have just comparing to stellar instruments. And so there are more variability between bands, though this is quite to be expected, considering the field of view and considering the challenges of matching them together. So next.
Okay.
And
Sorry, there you go.
we returned back in Alaska this summer and tried to measure and figure out how to measure the same plants again, this time without snow, or the same vegetation types. And so again, it's much more difficult to measure standing tall stature forests than grassland or crops. And so we keep trying, and we need a lot more inputs and people to tell us what are they measuring, how are they measuring it. And so this is more of a topics for our discussion. And together we need to figure out how to go forward to get comparable field measurements between stellars, between different vegetation types, and then stellars to field spectrometers. And so that's the direction we're going, like in the next year.
Mhm. All right.
Thank you.
Awesome. Thank you very much, Petya. Now we're going on to Ross, our data visualizer. He's a little tired in this photo. Ross, take it away.
Hello, everyone. Thank you, Mike, for the flattering photograph. My name is Ross Walter. I am the programmer visualizer for the STELLA team. And my main focus has been on creating a data viewer, which is a web-based viewer that you can upload your data to and do some graphing and some indices. So if you haven't seen that, I'm going to do a little bit of, oh, looks like I can't share my screen, so I'll just talk about it. But basically what you can do is you can upload your data to this web page and perform some indices. You can view it on a graph. Some of the updates that we've done to it, or I've done to it, is create a tutorial sequence. If you kind of see that in the top left, it says the batch section. It'll kind of take you through the experience, how to use it. We've also updated the help section along with our writer, Ellie, to basically describe each indice, how to use the tool, and some of the people who have helped put it together. And then currently we're updating some UI, just making it look a lot nicer and easier to understand. But very good progress with the data viewer so far. And then Mike, if you could go to the next slide, please. One thing I've been working on for outreach is making an AR card. So we've been handing these out at outreach events. It's got a little Instagram tag on there, so you can scan the tag and open it up in Instagram. And then on the far left, you see a video of what it looks like. And this has been really fun to make and really fun to share with people, just to get the word out about STELLA. On the back, it just leads us to our webpage where you can learn more information about how to build it, all the team members who are working on it together. So yeah, that's been some of the stuff I've worked on.
Awesome, Ross. Fantastic job. All right, and now we're going to go on to the inventor, creator, and again, all around fantastic guy, Paul Murrell. And he's going to talk all about the latest and greatest of what's coming up with Stella. Take it away, Paul.
All right. So can I have my slide, please?
Yes, you may.
All right. Thank you. Talking about what is available to you if you want to have a Stella, we have the Stella 1.1, which requires soldering and 3D printing. Each of the original versions of the instruments require soldering and 3D printing. The Stella 1.1 has 12 channels, 6 in the visible and 6 in the near infrared. We are moving toward the Stella 1.2 on the right there, which has 18 channels, which go from the UV down into the near infrared. Both of those instruments measure the remote surface temperature for an emissive surface and air temperature, humidity, and barometric pressure. And there are accessories you can stick on there to get a short range measurement using an inexpensive LiDAR. And then also we have a insert that you can put in that will hold a cuvette for doing liquid spectroscopy. In the middle, we have the Stella 2.0, which has the same 12 channels, but is Bluetooth enabled so that you can connect to smartphone. That particular version has the lightweight battery and is generally lightweighted for drone use. So you're looking at 68 grams of instrument and another about that much of housing. Next slide, please. Then for people who don't want to solder or haven't learned how to solder, we have a series of instruments that you can just plug in. They take about 10 minutes to assemble, even if you've never seen them before. So you assemble them and then you drop the software onto there and there you go. You've got yourself an instrument. The one on the left uses the same 12 channels as the other Stellas, and the one on the right, which we're working on, uses the new 8G channel sensor. So these both have the same spectral capacity of the more involved instruments in the first slide. And then in the middle, we just recently added an air quality instrument that measures the particulates in the air, and it measures the carbon dioxide in the air. So you can use carbon dioxide as a proxy for how well ventilated the space is, because if you've got a lot of people breathing in an enclosed space, carbon dioxide is going to go up. And with the particulates, you can get the air quality index for particulates. This instrument doesn't measure sulfur dioxide or carbon monoxide, which are also part of the official air quality index, but you get the particulate version of the air quality index. And again, all of these instruments, all 6 of these instruments, the cost for the parts is in the neighborhood of $200. So if you want one of these things, if you have $200 laying around, or can get a tiny grant for that sort of thing, you can build and use one of these instruments. So there we are. Thank you very much.
Awesome, awesome, awesome. All right, and with air quality in mind, we will turn it over to the newest person and a really awesome person as well, Dr. Nyssa Rayne.
Yay, thanks. So next slide, I'm Rayne. They took a chance on me. I came to them with a really wild idea to kind of put 2 different sensors on an instrument that don't typically go together. And so STELLA-AQ is an easy to assemble, no soldering required instrument designed for middle schoolers that measures carbon dioxide, particulate matter, both small and large, and weather variables. It's modular, so different sensors can be swapped out and shared amongst different classrooms, maximizing its usefulness as an educational tool, while also being simple and cheap enough that a middle schooler could pick one up and use it to explore the world around them. It also comes with an open source instruction guide, material list, and code with a support forum via GitHub, and is a great example of NASA's Year of Open Science campaign. We're excited to offer it as a low-cost portable tool and are exploring proposal options for funding a pilot study in classrooms. Well, I am. I don't know about them. They'll be on there too. But the whole reason I even went this route of carbon dioxide and PM 2.5 is I previously purchased my own meters and in advocating for clean air in my children's classrooms. And so we use CO as a proxy for room ventilation, while particulate matter serves as a proxy for how clean the air is. So that's why those two, and typically those aren't put on the same monitor, or they're not, done well. So I think that it was such a cool idea, and I really appreciate them taking the time to be open-minded with my crazy ideas that I come up with constantly. It's such a cool tool. The Stella just is a really, really cool tool. I wish I had it as a kid going through education because it's the hands-on components, and yeah, so big things happening. I'm excited to work with the group, and thanks y'all so much.
Awesome. Thank you very much, everyone. And a special thanks, of course, to Landsat, who we are under again, and Chris Nye and all that, Ginger, and, all of the folks that really have helped make this project really just come together and become something, incredible and special, and hopefully it continues. All right. And with that, I guess we'll turn it over to Q&A. So let me end the show here and let's see what we got. Okay. Stop share. There we go. All right. Okay. Does anyone have any questions? There's a Q&A. You mentioned Stella loaner program. How would we sign up to get a loaner? You can email me at michael.p.taylor@nasa.gov and ask, and I will go ahead and pop you into the sheet of people that have asked for loaners. Great presentation. Can you please expand a bit on the CO2 measurements from Manuel Lerndau? Nyssa, do you want to field that one?
Yeah, I can take that. So CO2 is there should be a metric easily accessible, like if you type in CO2, and it's being used more and more in indoor air quality to just indicate that you need to either open a window, because if it gets above, I think 2000, and I want to say it's Paul, help. What are the units on that?
Parts per million.
Parts per million. I thought so. So yeah, because it's a gas. So yeah, I have one in my house right now, but and it tells you green, yellow, or red, like open a window. Because so in classrooms where you have all these people crammed together, the CO2 they exhale like builds up, especially if it's not the air's not moving, circulating, and so. Oh yeah, see, that was a Paul question. No worries.
So he's asking how the CO2 is measured and with what sort of resolution.
Paul.
Okay, so the CO2 sensor is some really amazing technology. It is a photoacoustic sensor. So this goes back to something that Alexander Graham Bell did, where he had a little disc of metal that was painted black, and he put it in the sun, and of course it expanded a little bit because it got warm, and then he put the equivalent of a fan in front of it so that it would get sunlight and then not sunlight, so it would flash on and off, and he could get the plate to vibrate that way. So what this sensor does, so this little tiny sensor here, about a quarter the size of a sugar cube. Inside of it, there is a little near infrared laser that is tuned to the absorption spectra of carbon dioxide. And it flashes on and off at a frequency that is tuned to the size of the enclosure. So the carbon dioxide expands and then contracts. That creates a pressure wave. You do that over and over again and you create sound. And you do that resonant in the cavity. And then you have a little microphone and you measure the sound. You do some fairly sophisticated measurement technique to disambiguate from water, which has some similar absorption characteristics. But in the end, you get the carbon dioxide in the air to plus or minus 50 parts per million plus 5% of the total measurement. So the error bar goes up as you get a larger measurement, which makes perfect sense. So you can think of it as plus or minus 5% plus an additional 50 parts per million of uncertainty. So that's carbon dioxide for you.
Cool. Awesome, Paul. Next question. Any plans to integrate something like microfluidics into the cuvette version in the later versions, or potentially even a stir bar?
No plans for microfluidics right now. That's sort of outside of the level of tech that we're working with. We're trying to keep these instruments simple enough that people without a lot of technical expertise can build and use them. We are considering making a flow-through version of the instrument so that you can, say, strap it to the side of your kayak and measure the optical characteristics of the water that you're paddling through. That's a future idea.
And you have something, Jesse?
I mean, we don't currently have the specific people on our team that would make use of microfluidics or have that type of understanding. But anyone who wants to build a Stella, the cuvette holder is currently just this little guy, which slots in directly in front of our sensors. So, and there's space all over here. So if you have an idea and a 3D printer and the microfluidics stuff that you might want, or a tiny stir bar, go for it. There's nothing to stop you from integrating on our design and adding your own little things. That's part of what the GitHub and the forums are for.
Exactly what I was going to mention. That is a perfect example of what the GitHub is for, so that we can hopefully hook you up with someone who could collaborate with you on that and help you, build something like that, or, answer any questions you might have. So exactly. So check out the GitHub if you haven't done that. Okay. Any other questions? Oh, I got one right here. What can Stella provide to help with a local school grant program? As a starting point, to share with a teacher to see if there's interest and to provide content to the grant. Also, you mentioned NASA's Year of Open Science. Are there opportunities for schools?
I think we should point some of that at Nyssa.
Yeah, sounds about good.
Be like really quiet. No, I do know that NASA has Connects, which is a community of practice for teachers and educators. So it's CONNECTS. And so you can join, and they do it by grade level, so you can like get differentiation in there. I plan on putting some Stella advertising things in there too. And let me think. I'm trying to think of other resources. Yeah, if anybody else knows, they can hop on and tell it too. But I mean, there's Rose's grants I know available. I'm not familiar with like educator specific grants, but there should be some. Thinking back to like my master's in education, I was like, where did I go to get money? So I think there are some organizations and things like the National Academy of Science Teachers maybe is one of them. But yeah, that's what I got. It's my best answer.
Anyone else? Would be of help? No? So I guess probably the best answer we got at the moment. Does anyone else have any other questions? No? All right. Well, I guess if we don't have any other questions, then we can end the webinar. I'll give it another half a second here, see if anyone else comes up with anything. If not, we're good.
When will be the next one?
The next webinar, that's a good question. I don't know. So again, these are not going to be like a regularly scheduled thing. You know, it's when you know, something you know, when a few big things come up, you know, like say the STELLA-AQ, you know, Nyssa joining the team, you know, Ross yawning again. I don't know, and me capturing it on picture. So, you know, we'll see what happens. So other than that, again, if there are no more questions, let's see, Trung Tran has his hand up. Yes, can you type in your question?
Do we have the ability to allow them to talk?
Oh, allow you to talk. Yeah, we do. We do have the ability. You can talk. Okay. Sorry, I'm still figuring this thing out, and Jesse spotted
Do
it.
you hear me?
Yeah, I can hear you.
Oh, thank you very much. So sorry, I had a meeting just came up just before this one, so I came like 30 minutes late, so very late. So I'm just wondering, have you do we have a recording of this session so
Yes.
that I can review?
It is-
Okay, I appreciate it. Thank you.
Not a problem.
Will that be posted on the GitHub or where will that be posted?
Yeah, I'll make sure and post up actually both webinars and pop it up on probably the website, or yeah, and so that people can see it. Okay. And I'll make sure
That's
to email
excellent.
it out as well to all the enthusiasts. Okay,
Wonderful.
cool. Anyone else? Questions, thoughts, concerns? All right. Well, we'll wrap it up there. And thanks again, everyone. You all were great. And we'll see you at the next webinar, whenever that might be. Bye.
Bye.
Take care.
Happy Tuesday. See y'all later.
Yeah, buddy.
It ends.
Or just stop recording.
Yeah.